Today's problem is three tanks in series, and we're going to be deriving equations for the fluid levels, specifically for this third tank right here. That's what we care about most. Well, none of these tanks we want to flow over, but all right. So, as you may remember from the Conical Tank video, if you saw it last time, from Bernoulli's equation, we have. Let me start out like this. We've got dV over dt, and that is equal to the cross-sectional area of this tank times dH dt. And we really care about this dH dt term here. So with that set, we also got b squared over 2 is equal to g times h from Bernoulli's equation, and math that out to be v is equal to the square root of 2gh. Also, we do have to have the size of the hole, so ah, the size of the hole of all of these, which we're going to assume is the same for coding. That'll be later in this video. So q in that we will determine with a proportional control later. I'll add that. That's going to be the final step of this. But so far, we have Q1 is equal to the AH by the square root of 2G, the height of the first tank. Q2 is equal to AH times the square root of 2G and the height of the second tank. Q3, or Q out as I've called it, is equal to AH times the square root of 2g and the third height of the third tank. And with those equations, we can put that into code later. All right, so we want to get the mass balances out of the way. So we know that dV over dt is equal to Q in minus Q out. So for the first tank, we're going to want to pull out the AC term and put that under here. So we have dH over dt is equal to Q in minus Q out over AC. And that's going to be the basis for all three of these tanks. So then we have dH dt of the first tank is equal to Q in minus Q1 over AC, and then dH2 over dt is Q1 minus Q2 over the cross-sectional area, and then dH3 dt is Q2 minus Q3 or Q out over the cross-sectional area. And we can replace each of these flow terms with each of these terms. I'm not going to do that here. I'll do that in coding. But yeah, so each of these terms would end with one of these. Minus, Q out, Q3 would be that too. So everything but Q in. And that pretty much sums up the derivation for these three tanks.
We've got the three tanks in succession, and now we're starting to code them. So I've got all these for the same reasons as last time. Numpy for everything general, plotly for the plot that I'm going to make, and solve IVP to solve the equation that I make at the end. And I have these written down here. Let me show you that notebook so you don't. I forgot to do this last time. I just got all my notes written down so I wouldn't forget when the board was erased. Got the size of the inlet holes is equal to 0.01. We've got the cross-sectional area is equal to 1 meter, or 1 square meter. And we have Q in initial is equal to 0.1. And then we have the H naught, which we derived from the conical equation, is equal to, let's see, get some parentheses in here, Q in over AH squared over, no. Yeah, I guess you could do that, or you could just do 1 over 2 times G. Alright, and there we go, we're good. Well, wait. And time, it's going to be 5,000 seconds to start. I do believe that is all we need for right now. Alright, and now we're ready to make the equation. So we need to define a tank series. I was going to call it tank for simplicity. And then have it be tank with respect to t. And then I think we need a vector because we've got 3 different heights instead of just 1. I always forget the colons. H1, H2, H3 is equal to V. We need the Q1 flow, Q1, which is out of the first tank. And so we're defining it as, Q1 is equal to, I have it written down here as well. Let's see, AH times 2 times G times H to the 1/2 power. Q2 is equal to as well AH times 2GH Q3. Wait, I'll put it in a minute. I need to do the actual heights of these. So Q3 or Q out. And this is going to be H3, you're going to be H2, and you're going to be H1, and you're all to the 1/2 power. And then, I might be missing a step here, but we need to return, I know we need each of the derivatives, which I also got written down, so it's, don't know what the t term is at the moment, but we've got Q in minus Q1 over AC plus Q2 over AC Q3, and I think I actually missed a step. No, I know what I did. I need to define Q in as Q in equals Q in not times 1.2, because we're doing a 20% increase for this. I know what I did wrong. It needs to be an array, because if we don't have it set to an array, then it'll be messed up. Here's to hoping that works. I guess let's run everything and see. Yay! More problems. You need that, don't you? No, that's not it. I see it. Ah, Silly me. Didn't even define gravity. There we go. Alright, looks like the equation's starting to work. Okay, so we need the result to be solve IVP, and we need that to be let's see, tank time span 0 to t. We need the array of h naughts, or h's rather. So we got H1, H2, and H3. And then this isn't completely necessary, but we're adding the method is supposed to be, oh boy, the method is supposed to be equal to radal and dense output. To true. Of course. I had to find it up here, didn't I? Isn't that what this is supposed to be? Alright, this is fun. Oh, I guess this is an initial value problem, so these are all H naught. Because all these tanks are the same. Okay. More code, and I think we're ready to start plotting. Alright, so we need a plot is equal to numpy linspace. And we're going to go from 0 to 500. Or 0 to 5,000 with 500. I did this last time where I messed it up a little bit, and I got the last two terminology things wrong. Hey, and I am pointing at the screen and you can see it. So 0t and 500. So 500 points between those 5,000. And then we've got big equals make underscore subplots. And then we've got add scatter, and that's gonna add scatter x equals plot, y equals leave h1. You might need something else there, but I'm going to go ahead and go Sankey. I don't even know what that means. You know what would be faster than just typing these out? I could just copy paste, so I'll do that for the next one. And then just change it to H3. So we're good with that. I think that, nope. H1's literally defined up here. I don't know what more you want from me. Okay, maybe I do have to redefine these. I think I have to unpack them is what it's called. And then we need, well, we obviously want the result of the solve IVP, so dot solution, maybe, no, gonna unpack it. It is iterable. maybe with respect to the plot. I don't know if that'll change anything. Oh, of course it did. And of course, I don't actually know if this is right. So I guess we'll see. I think this is right, but before we add the proportional controller, because you would need a proportional controller, otherwise all these tanks would be overflowing. But it figured out the set point's supposed to be around 5 something. They all got the steady state, so I've got something that works here. Alright, to the best of my knowledge, this stuff is exactly as it needs to be. In the next part, we'll just add a proportional controller to this to make sure the tanks don't overflow, because I believe they are set to the height of 6. Could be wrong. We'll see.